this on or am I? Yep, okay.
Okay.
Great. Okay, so I'm going to talk about open science and reproducible research and how free and open source software ties in really well with the concept of reproducible science. I'm Bill Hoffman. I'm a CTO, one of the founders of Kitware. One of the big open source projects I created since I've been there is the CMake project. It's a build system. I also like barefoot running. Okay, let's talk about that later. So Kitware is an open source scientific computing company. And I'll go into that a little bit more. I'll give a quick intro to Kitware just so you have an idea. How many people have heard of Kitware? Yeah. How many people haven't heard of Kitware? There we go. Good. So this is sort of the quick slide we give about what Kitware does. And we've got a supercomputing visualization group, a medical imaging group, a computer imaging group, data management, and this is all tied together with a software process core. And one of the things that makes the company unique is it's all open source. So what this shows on here are all the various open source toolkits that we use. The visualization toolkit, that was one of the founding parts of the company. The company was actually built around supporting this visualization toolkit. And then out of that came ParaView, which is a turnkey application that's all open source, used a lot by the national labs to do supercomputing visualization of really large data sets. We've also got a medical imaging group, there's a whole bunch of open source software there. Insight Toolkit, Slicer, Volview, Image-Guided Surgery Toolkit. The Computer Vision Group uses a lot of open source software, doesn't actually have a tool that they sort of claim as their own right now. Inside the software process, we've got CMake and CDash. And then we've got a tool called Midas for doing data management. This is the software process. And we'll go into a little bit of history of this later in the talk. But the basic idea is having a process where developers write the code, check it into a repository, it gets tested somewhere, and then the results can get sent back to those developers. And this is really key to developing quality open source software. So here's just a few slides on our supercomputing visualization. There's a scientific visualization, which is taking scientific data and looking at it. Another interesting area where we're starting to grow is analytics and information visualization. Taking data that traditionally isn't something you can render. I mean, if you look, like right here, this is airflow around some sort of pin. I think it was part of the original space shuttle. And it's something that you can figure out how to render on the screen and give as a picture to people. Whereas if you're looking at some sort of network of people around the world or other types of information that don't directly lend themselves to physical representation, that's sort of the information visualization. That's a pretty hot topic lately. We've also got a big move for open chemistry, creating tools for visualizing and doing computational chemistry and accessing supercomputers. The medical imaging group process, analyze, and visualize medical data. Image analysts operate an image to extract information. Segmentation, identify features in an image. And registration is to align images. So you might have a CT image and an MR image from the same person, and you might want to figure out how they lie on top of each other so you can do better automatic analysis. Recently, we've been working with OSERA, the open source health records, and applying our software process to these tools and working with the Vista project. And this is and using sort of all of our tools that I'll be talking about. We're also working on mobile technologies, so there's a open source viewer for various mobile platforms. We've got an example, we're working on a digital pathology application where you can look at slides and look at these really big data sets. We're also moving towards cloud technologies. We've got a ParaView Web, and again, most of this stuff is open source, or almost all of it. And the idea here is to take our end user sort of pair view application that we've traditionally had and turn it into something that can be used inside a web browser and give access to a large supercomputer and allow the rendering to happen there. It's my computer.
Is this PowerPoint or open source?
It's PowerPoint. I haven't plugged in on the last I haven't copied it to the desktop. Let's see what's there. I don't think the copy actually. Yeah. Yes. Just start with that. I got it. Yeah. Yeah, it gets stuck on this slide. What?
We'll go past that slide then. I guess it gets stuck on that slide. Does it have extra? There may be a delay in the
It should.
Can you go past it?
Oh, you know what? It's probably the next slide that's causing trouble. Can I just try to plug it in?
Yeah.
Yeah.
This is.
Yep. Okay, we're back.
Is this the slide that was causing all the
This is the
problems?
trouble. Yep, and it works. Okay. So we also have a computer vision group. Their main area of interest is wide area persistent surveillance. So the idea there is they have big cameras now that they can fly in planes or unmanned vehicles, and they look at a big area, and the idea is you can track movers and vehicles and try to find interesting things that are happening without having people look at it. Status of the company, we were founded in 1998. We've got locations now in Clifton Park, North Carolina, and Lyon, France, and actually we have one in Albuquerque, Santa Fe, New Mexico right now. 5 founders who are previous employees of GE Corporate Research and Development. Yeah, I'll move on. So, what I'm here to talk about really is science. You know, that big scary thing, science. So going back, 1630s, the scientific method, basically doubt everything and believe in things that are evidently true. Reproducibility. The Royal Society, if it's not reproducible, it's not science. So how did this work? So the scientists, they would write their letters, send them to the Royal Society, people would experiment, reproduce. Once it was reproducible, they could create a transaction, they could publish this, it would go around the world. So eventually they came up with the scientific method where you come up with a theory, you experiment, and you have data, and everything sounds good. Eventually eventually it evolved into this, where scientists, they write papers, they're peer-reviewed, they end up in journals. There's some problems with this model. Creates career pressures. So the author, publish or perish. And that's what they taught me in graduate school. So it's more important to get the paper out than to worry about, is this reproducible? What am I worried about reproducibility? Is that part of the culture? It needs to be part of the culture. Another interesting thing is that science is becoming computation. So a senior NSF director said that software has replaced mathematics as a modern language of science. Obviously, it's the encoding of mathematics in computer programs, but the point here is that much of scientific research is happening in code. So that all sounds great, So instead of writing a mathematical formula, you encode it in something that looks like that. But this is the code. This is what people need to see in order to reproduce it. They need to see it, they need to be able to run it. But unfortunately what's happening, we've got publishers and they come with theory, and then if people are using closed software and data that people don't have access to, the reproducibility is almost impossible. So what tends to happen, let's see, I've got another slide and then I'll move on. So publishing in the modern age. So as technology moved forward, of course, there's always industries that fall behind, and we're at a junction right now. So today, to post a PDF file to the web takes about an hour, and it doesn't really cost much, about zero marginal cost. Time to publish a paper in a journal typically takes 2 years. Cost to publish it about 500 euros a paper. I gave this talk in Europe, that's why it's got euros. Cost to read the same paper about 30 cents per paper. Does this make sense today? Now, it made sense when the only way to get the information out was to print it. And there was a great synergy there between the companies that invested in buying a big, huge printing press, one of these things, and then the scientists would work with them, and they would make enough money to cover their costs and pay their people and make a little bit of profit along the way. But times are changing, and the business models need to change. And we're seeing a failure of reproducibility. So in the March 2012 Nature, the head of cancer research found that 90% of the papers published in scientific journals describing landmark breakthroughs, preclinical cancer research, are not reproducible. And thus, are probably just plain wrong. So that's kind of scary. Are you scared? I'm scared. So here's an example of a challenge. So this was at a medical imaging conference, and they had a reproducibility challenge. So they had 8 international teams participated, and they were just created 3D visualization comparison of different tractography using the same diffusion MRI data set. This is where the tracing the white matter tracks in your brain. The results of the workshop were this. How do you compare them? It's tough. So, in a sense, that's kind of a failure of science. How do you reproduce it? Which one's better? So, what I want to talk about is the better way of doing this. So, open access, open source software, and open data. And open science. So I'm going to talk a little bit about CMake, my project, and its sort of history in open science. The United States has NIH has the Visible Human Project. How many people have heard of the Visible Human Project? Okay, so this was a project funded by National Institutes of Health. And it was a neat project. They took a body that was donated to science, and after they died, they CT scanned, an MR scan, and saved these data sets, but then they also did something. They froze the body solid and then sliced it as thin as they could and took pictures along the way. So imagine you're an algorithm writer and you're segmentating the heart out of a CT image. How do you know you got it right? How do you know your science is reproducible, that you've done the right algorithm? Well, one way is to cut them open. Usually you can't cut the patient open. In this case, you can because the patient's been pre-cut open, sliced, and taken pictures. So they put this data set out, and that's great. And then some people at NIH, Dr. Terry Yu, had the foresight and vision to say that, well, okay, the data set's out there. Now we need the algorithms. What's the state of the art in segmentation and registration algorithms? And can we codify that in an open source library? And he started the initiative to create the ITK, the Insight Toolkit. Kitware was part of this team. And the idea there is to avoid the problem, like what happens today typically is a graduate student, their professor reads some paper and says, this looks like interesting research. Can you go try it? And the grad student goes off, types in his computer, hacks away, comes back 2 months later and says, nope, didn't work. Did he or she implement the algorithm bad? Did they use the wrong data set? Was the original paper wrong? If you can't get your hands on the code and the data they used to write the original thing, you have no way of knowing. So the idea of this project was to do that. And part of it was to create a build system that worked across all the platforms so that the C++ could be built anywhere and used anywhere by anyone on the project. So there is some advances going on in reproducibility. So some work at Kitware, we've created an Insight Journal, which ties back to the ITK project, since about 2005. And the idea is that submission and automatic code review. So the author would create a PDF document, their paper, plus the code, plus the input data, and the expected results data. Check this in as a paper, then it would automatically run that suite of tests that the user put in, send it off to a dashboard, and that would be sort of the first review that showed up in this journal. It's the automatic, yeah, it ran everything. It's been running continuously for 7 years. It's got, I think, 536 published articles, 802 reviews. So this is an example of how it could work and how it does work. We also, it's a lung cancer lesion sizing toolkit example. So these are taken at different points along the time, and we want to see that the measurement of the tumor isn't changing, or isn't changing over different scans. And again, we're using that same technology to create lesion sizing toolkit, where people can write papers and upload their data. And there's people outside of Kitware doing this. There's Run My Code. The idea is researcher has an idea, writes a paper, using Run My Code, creates a companion website associated with the paper, allows people to implement the methodology presented in the paper. So, science is not being done by one person. The problems are getting bigger, which is another forcing function in the open source movement, and the people actually doing this work want to get their work out and show that it's reproducible. And it's a forcing function in that to create a product today is very complicated. I mean, sometimes it starts all the way down at the atomic level, using visualization, nano level, bundle level, and properties all the way on up to the macro scale. So it's getting more and more complicated to do things, and it's going to require different approaches, more collaboration, and more access to the data and the methodologies used along the way. Basically the same thing here. So analysis, simulation, optimization. This is using a pair view. So there are signs and calls for change. So I found this article, Shining Light on Black Boxes, Publication in Open Knowledge, a material from Backbone of Science project. Although I thought this was kind of cool when I tried to get the article. It was behind a paywall. The Public Library of Science PLOS Open Access. This was an effort to fix this problem, and it's got quite a few articles in it now. You can probably look it up after this talk if you're interested. The World Wide Web Creator Season Access and Future for Academic Publishing. Activists pushing for open access will eventually defeat the publishers. But there are issues with that. Science is based on building and reusing openly criticized, published bodied scientific knowledge. For it to affect the science data, it has to be open. There's sciencecodemanifesto.org. Think about the code, the copyright, the citations, the credits. The National Institute of Health came up with a public access policy. Essentially, if your tax dollars are going into this research, they're saying that it has to be open. So a forcing function, a lot of people are getting, a lot of this research is being paid for by tax dollars. So there's a real issue of you have to pay to actually see it. It should be free because you already paid for it once and you paid your taxes. And other places are having open access policies as well. I found this pretty neat place, the worldmap.espirits.org, Registry of Open Access and Mandated Archive Policies. And you can see since about 2004, it was pretty small, but it's starting to grow that institutions are demanding that publications that they're funding are open access. There's some economic repercussions. So the subscription costs are getting out of control. Harvard University canceling 2 expensive journal subscriptions due to expense. UK, the Ministry of Science, all public funded research should be open access. World Bank, there was a big boycott of Elsevier. A project that Kimmer became part of from DARPA called XData. It's a project for doing information visualization. And this was in the call for that proposal, which you wouldn't expect from something like DARPA. You think secret projects going on all over the place. Plans to release open source software toolkits to enable collaboration among applied mathematicians, computer science, and data visualization communities in order to facilitate the transition use across enterprise platform. Unlimited rights and public access, open source is strongly encouraged. Scientists can learn from sort of the software developers as well. So this kind of goes back to my tenure at GE Research and Development. And they had a Six Sigma process that came through. Anybody know what Six Sigma is? A few people. And the idea is basically that you want to get your errors and defects in the Six Sigma area of the curve. And when they came to us and said, Jack Welch said, hey, this looks like a cool idea, and you have a big company like GE and you want them to all go one direction, you say, well, everybody has to. So everybody in the company had to take Six Sigma training, and there were a bunch of researchers at the research center, and it's like, well, we write code and we throw it away, and we write papers, and how does this fit for us? But what came out of it was really cool, was the concept of a software dashboard. And this still goes on, and we're using it in kitware. Things we can measure, like number of tests that pass and fail, number of build errors and warnings, and we can constantly measure this stuff. And we applied that and took that sort of draconian, you will do Six Sigma, and figured out some way to make something pretty cool out of it. And we're still doing this, and this process really applies to open science as well, this idea of reproducibility and measuring defects, and it can be applied to science. So the software process essentially produces reproducible results. The developers, they write their code, they check in the repository, there's testing. This process can be applied to science, and should be, in my opinion.
Oh, no.
I'm fine.
Alright.
so so what's stopping all this? Well, there's some roadblocks. So, in one paper I read, the world colleges now collectively spend at least $10 billion and probably more than $20 billion every year in subscriptions. That's a lot of money. Someone's making all that money, and a lot of people are getting paid. So, a big shift has to happen. So that's a huge roadblock, and these people have to figure out how to remain relevant and, provide value added and still stay in business. In some sense, because it's been like the way it is, the publisher perished, and reproducibility is not part of the culture. You don't necessarily move ahead in your career because your research is really easy to reproduce. You move ahead in your career because you publish in famous journals and have people citing you a lot. There's not a feedback loop. If the student finds a method in a paper failing to work, there's not a really easy way to get back to the author. You could try to publicly discredit them, and say, well, this is bogus research, but most people don't go to the bother of doing that. But there isn't really a good feedback loop, and that's part of the problem as well. And there's not a lot of money for software infrastructure. Everybody just wants to spend things on the research. And again, science is becoming computation, so the two are sort of tied together. Obviously, this was a big public case. Aaron Day downloaded all the papers, never published them anywhere, but got in a whole lot of trouble just for doing that, and it ended really, really badly. But hopefully there's definitely some calls for change after this. Aaron's law proposes changing the federal anti-hacking statute. Free and open source and science have always had sort of a close relationship. And I like to notice this, and we've done a lot of work with research labs around the world even. And what I've noticed is, I think that the scientific community is sort of this engine behind open source that a lot of the open source community or people looking at open source don't realize is there. To this day, the US Army remains one of Red Hat's largest customers by volume. Open source, a lot of open source comes from scientific groups. There's, LINPACK benchmarks are the measure of a system's, that's how we measure how powerful the world's supercomputers are. And that's an open source package. CERN is launching an open source hardware effort. So, and ever since I started at the Research Center, we did a lot of open source stuff or like that where we shared code. So I definitely think the two are related. So open source software, reproducible code, marriage of free and open source software, open data, open documentation, open code equals reproducibility, which is the scientific method. That's the end. Any questions?
Yeah, we have time for some questions.
I have a story. Paul Krugman is a field where people are arguing for stimulus spending. He's against a lot of, mostly Republicans, who want cap spending. There was some paper which was published by a couple of economists from Harvard. And their paper, Harvard said, once you go over 90% of your GDP, that growth rate slows down. And the graduates of UMass decided he wanted to make the data, so he emailed a couple of times. Finally, he got into the Excel file back. He ran the data and found out the place in Harvard was wrong. So, in terms of having available data, since the data, there's nobody tracking it. So the graduates, so the idea to build software and data, because they had a lot of people in Europe, in Greece, in Spain, Wisconsin, a lot of gas. Make sense?
Okay.
Look at your data. Right on.
A question following a comment. I had mentioned before about trusting open source, and I really do trust it. Does it make sense when people say, no, you can't trust open source, don't use it, you can't trust it, but look at how much we use open source in servers, file servers, right?
Yeah.
Very high. So can you explain, what's the difference? Why do we trust it so much with file servers, but not, for example, on this campus where Bill Gates becomes the second richest guy in the world?
Right, we're using our phones. I mean, I think that this stuff changes over time, and there's certainly standard issues. I'm using PowerPoint here. It depends on the models. These things change over time. I mean, the computer industry is reluctant to change. I mean, as much as you want to beat up Windows, it really created something that allowed like programs to be run. I can still take a program that I wrote 10 years ago and run it on Windows 7. That's kind of cool. That's sometimes hard to do on Linux system. So I'm not sure I'm answering your question.
Does it make sense though? If they say next year, 1 year from now, Windows XP won't be supported. You can't use XP after April of 2014. Why not?
Well, I think the answer to that is look at your requirements, right? And if you can look at your requirements, look at the available software, and if your requirements aren't met by something open source, well, you can either add on to something it is and develop it yourself, or maybe you have to buy something commercial. I mean, that's just sort of a need basis, and this stuff will develop over time, and as more needs are met. Any other questions? I think we're out of time.
Yeah, that's it. Thank you so much.